Hello everyone, welcome to our mathematics presentation on hypothesis testing by our group, which includes roll number 71 to 81. In this presentation, we are going to discuss what is hypothesis testing, types of hypothesis testing, its examples, test statistics, case studies, types of errors, critical region, critical value significance, effect of the critical value, effect of the sample space, one-tailed test, two-tailed test, and their examples, confidence interval, hypothesis testing using p-value, value of a test, power of a test, and at last, examples including all of our concepts. So now let's start with what is hypothesis testing. In general, we make decision about population on the basis of sample information. But in hypothesis testing, an assumption is made on the population, and by going through some statistical analysis of the sample information, the validity of the assumption is tested. For example, we decide on the basis of sample data whether a new drug is really effective in curing a disease. Any assumption taken on a population regarding its probability distribution or its parameter is called hypothesis testing. Such a hypothesis may or may not be true. For example, let we assume that the mean of a population is 60. Then mu is equal to 60 is the statistical hypothesis. Drawing the samples from this information, we can test the validity of this hypothesis, and this is hypothesis testing. Hypothesis testing concerns on how to use a random sample to judge if it is evidence that supports or not the hypothesis. To prove that a hypothesis is true or false with absolute certainty, we should need absolute knowledge. This is, we would have to examine the entire population for this.
My name is Aditya Singh. I will explain about type of hypothesis testing. First of all, it is formulated in terms of two hypotheses. The null hypothesis, let it be H0, and the alternate hypothesis, let it be H1. Let us check for H1 is true. For it, we have two outcomes. First, reject H0 and accept H1 because of sufficient evidence in the sample in favor of H1. Second, do not reject H0 because of insufficient evidence to support H1. Let me make it clear. Rejecting H0 does not mean the null hypothesis is true. It only means we do not have sufficient evidence to support H1. Example, in a trial, let H0 be defendant is innocent and H1 be defendant is guilty. H0 is rejected if H1 is supported by sufficient evidence. Failure to reject H0 does not imply innocence. It only means that the evidence is insufficient to reject it. Thank you.
Hello everyone, I am Tanibha Majumder. Today's the topic of my presentation is test statistic. First of all, we should know what is test statistic. Test statistic is the statistic where we take the help of a statistic whose sampling distribution is known by evaluating the value of the statistics. We decided whether null hypothesis is rejected or not. So, here is an example. In this example, we can see that defective rate of the population is 5% and the true defective probability is denoted by P. So, H0 is to P equal to 0.05. It means that the null hypothesis is equal to the probability and H1 is to P greater than 0.05. It means that the alternative hypothesis is greater than 0.05 or probability. Now we are going to use a sample of 100 chips from the production to test. Let x denote the number of defective in the sample of 100. Now rejected H0 if x greater than 10. In this diagram, we can see that the gray portion of the part where null hypothesis is rejected and the left side where H0 is don't rejected. So the value 10 serves as a boundary between the critical religion and the non-critical religion. Finally, we can say that this value of 10 known as the critical value.
Good morning everyone, this is Saumyodip Chatterjee and today we're gonna talk about the type of errors that we may commit when we do hypothetical testing. Now as we have to do this test or the testing in some finite samples, there is always a possibility that we may commit some mistake. Now, these errors can be classified into two types. One is type 1, another is type 2. Now, when we talk about this type 1 error, it's a kind of error in which we accept the alternative hypothesis even when the null hypothesis is true. This is like convincing the defendant when he is innocent. He is innocent. Now, this type of error, that is type 1 error, can be also known as the level of significance, and it's generally denoted by alpha. Now, to commit low amount or less amount of errors in our testing, we always want our value of alpha to be less or equal to 0.05. Now let's talk about the type 2 error. Now what is this type 2 error? It is a kind of error in which we fail to reject null hypothesis, that is H0, even when the alternative hypothesis, that is H1, is true. Now this type of error is can be denoted by beta, and committing this type of error is gonna decrease the clarity and the goodness of our testing. Now, most importantly, quote unquote, it is impossible to compute beta unless we have some specific value of alternative hypothesis, that is H1.
Good morning, sir. I am Taniya Ghosh from CSE. My roll number is 79. I would like to talk about the topic critical region. Critical region is defined as a set of examples for which null hypothesis is rejected. As we can see in the diagram, the critical value significance mainly provides a trade-off between the alpha and the beta. A reduction in beta is always possible by increasing the size of the critical region, but this also increases alpha. Likewise, reducing alpha is possible by decreasing the critical region. I would also like to mention some effects of the critical value. So as we can see in the case study 1, we see that the critical value from changes 10 to 8. That is, we reject h naught if x is greater than equal to 8. Also, as we move to the third case study, we see testing against the alternate hypothesis h1 is to be equals to 0.1. So according with the formula, beta gives us 0.206, which is lower than before. Testing again the alternate hypothesis h1 is to be equals to 0.15. So according with the formula, beta gives us 0.012, which is again lower than before.
Good afternoon, sir. I am Biswas from CSE, roll number 81. I am going to discuss the effect of sample size on alpha and beta. Both alpha and beta can be reduced simultaneously by increasing the sample size. From previous example, we see that the value of n was 100. If we increase the value of n from 100 to 150 and the critical value is 12, then we will reject h0, the null hypothesis, if x greater than equals to 12, where x is now the number of defectives in the sample space of 150 chips. So the significance level of alpha equals to probability x greater than equals to 12 when p equals to 0.05. By calculating it, we can get the alpha value as 0.074, which is much lower than 0.128, that is the previous value of alpha when n equals to 100 and critical value was 8. Now if we calculate the alternative hypothesis h1, the value of beta becomes probability x less than 12 when p equals to 0.1. By calculating it, we get the value of beta equals to 0.171, which is also lower than previous one, which is 0.206.
So let's talk about the summary properties of hypothesis testing. alpha and beta are related, decreasing one generally increases the other. The second point is alpha can be set to a desired value by adjusting the critical value. Typically, alpha is set at 0.05 or 0.01. The third point is increasing n decreases both alpha and beta. And the fourth point is beta decreases at the distance between the two true value and the hypotested value increases.
Good evening, sir. My name is Ritika Mukherjee. I am from CSE roll number 80. Here I am to explain one-tailed and two-tailed test. One-tailed hypothesis tests are also known as directional and one-sided test because you can test for effects in only one direction. It has no capacity to detect an effect in other direction. If we consider a normal curve and the population mean at the middle of the curve, then the sample mean can lie in the red region or in the non-red region noted in the slide. The red area is called as critical region or rejection region. The probability of sample mean being in critical region of any side is 5%. This value is noted as alpha or p-value, where the probability of being in non-critical region is 95%. In one-tail test, the critical value of right side critical region is positive 1.6 and for the left side is negative 1.6. Statistics. A two-tail test is a method in which the critical area of distribution is two-sided and tests whether a sample is greater than or less than a certain range of values. Two-tail test sample mean can be present in both right and left side of the critical region. Probability of the sample mean to lie in the critical region is 2.5%. This is the half of one-tail test. And the probability for being in non-critical region is 95% as same as one-tail test. Critical value for two-tail test is positive and negative 1.5 for right and left side respectively. In this slide you can see an example also for your convenience.
I'm Riya Chatterjee, roll 71. Now I'm going to explain about confidence interval. Confidence interval is a range of values we are fairly sure our true value lies in. It's simply a way to measure how well our sample represents the population which we are studying, and the probability that the confidence interval includes the true value within a population is called confidence level of confidence interval. Now here it is shown that it is 95% confidence interval. It means that we are 95% certain contains the true mean of population, and accordingly there is 5% chance that the population mean lies outside of upper and lower confidence interval.
Hello, this is Majumder, roll number 73. So today I am going to discuss about the hypothesis testing using the p-value. This is an alternative method to do the hypothesis testing other than the standard method. So first of all, I'm going to read the slides, then I'm going to explain it in a more simpler way. In the approach we have taken so far, the significance level is pre-selected up front, either by choosing a given value or setting the critical region explicitly. In this case, the final outcome is the decision. Now suppose a hypothesis test is performed at a significance level of 0.05, but someone else wants to test with a stricter significance level of 0.01. This requires recomputing the critical region. The p-value aims to provide more information about the test statistic with regard to the hypothesis test. Now here comes the definition of p-value. The p-value is the lowest level of significance at which the observed value of a test statistic is significant. That is, one reject the null hypothesis. And here an alternative interpretation of p-value is given. The p-value is the minimum probability of type 1 error with which the null hypothesis can still be rejected. Now here a graphical representation of p-value is given, and it is obviously an right one-tailed test. And for every test, first of all we have to always define the confidence level. Let here the confidence level be 95%. So the significance level will be 0.05, that is the alpha. And in this diagram, the alpha is the area in shaded region and the red region together combining. So from statistical table, we can easily get the critical value of Z, that is the ZC, by putting the value of confidence level, that is the 95%. Now we calculate the test data, and if the test statistics Z lies right toward the critical value of Z, then it will reject the null hypothesis, since it doesn't includes in the rejection area. And if the test statistic lies towards the extreme left of the critical value of Z, then we fail to reject the null hypothesis, since it doesn't lie in the rejection area. Now, p-value is the probability of getting Z more extreme right or left to the given data. To find p-value, first of all we have to look for Z, and from there we have to travel towards right, and the area covering up that is the p-value. That means if the test statistic is Z and it is shown in the diagram, and we move towards the right, so the red shaded region is the area that is covered up, and this red region is the p-value. So in this diagram, the p-value is less than the significance level, since the significance level also includes the shaded region side by side the red region also. So the p-value here is less than alpha. So in this case, it will reject the null hypothesis. And if the p-value is the greater than alpha, then it will fail to reject the null hypothesis. And an example is given here. Suppose that for a given hypothesis test, the p-value is 0.09. Can the null hypothesis still be rejected? Now, this completely depends on the significance level. If the significance level is 0.05, that means the confidence interval is 95%. We cannot reject the null hypothesis, since in this case the p-value exceeds the alpha value. However, if the alpha value or the significance level is greater or equal to 0.09, then we can reject the null hypothesis. Another example is given. A batch of 100 registers have an average of 101.5 ohm. Assuming a population standard deviation of 5 ohm, test whether the population mean is 100 ohm at a level of significance 0.05. And the number 2 is the compute the p-value. So in the first part, first of all we have to define the null hypothesis, that is mu equals to 100, and the test statistics is x bar. So it is a two-tailed test, so we have to find the lower and upper boundary of the critical region, and which after calculating we get that it is 99.02 and 108.98 respectively. and the x bar is 101.5, which lies far more right towards the upper boundary. So it rejects the null hypothesis since it lies in the critical region. And here comes the second part. To find the p-value, first of all we have to find the z value. Here z equals to x bar minus 100 by sigma by root n. Sigma is a standard deviation, n is the sample size. After calculating, we get that the value of z is 3. Now putting the value of z in the statistical table, we can find the value of probability of z greater than 3, which is 0.0013. Now p value here is 2 into probability of z greater than 3. Why it is multiplied by 2? Since it is a two-tailed test, so the critical region lies both the right side and the left side. So p equals to 2 into 0.0013 equals to 0.0026, and here the p value is very less than the significance level, that is the alpha. So the null hypothesis gets rejected. And here the graphical interpretation of the two-tailed test is given. The lower boundary is 99.02 and the upper boundary is 100.98, and x bar lies far more right towards the upper boundary, that is 101.5. And a point to be noted that the area equals to 0.025. It is the area of the significance level, and the area which is given by 0.0013, it is the area of p value. Therefore the area of p value is less than the significance level, so the null hypothesis gets rejected. Thank you.
Greetings, sir. I am Bhowmick from CSE roll number 78. I am here to talk about the power of a test. So let's start with what power of a test is. Simply put, power is the probability of not making a type 2 error. Let's go on with more on power. Power is the probability of rejecting the null hypothesis when in fact it is false. Power is the probability of making a correct decision to reject the null hypothesis when the null hypothesis is false. Power is the probability that a test of significance will pick up on an effect that is present. Power is the probability that a test of significance will detect a deviation from the null hypothesis such a deviation exists. Power is the probability of avoiding a type 2 error. So from what I have discussed previously, mathematically, power is 1 minus beta or 1 minus probability of type 2 error assuming H1. The power of a hypothesis test is between 0 and 1. If the power is close to 1, the hypothesis test is very good at detecting a false null hypothesis.
So here is a numerical. Let P denote the probability of getting hit when a given coin is tossed once. Suppose the hypothesis H0 P equals to 0.5 is rejected in favor of alternative hypothesis H1 P equals to 0.6. If 10 trails result 7 or more head, that means the null hypothesis is rejected when there is 7 or more head. Calculate the type 1 error and type 2 error. Now since a coin is tossed, that means it is a binomial distribution. So here is the answer. Let x denote the number of head in 10 tosses. So x follows binomial distribution of 10, p. Now we know the type 1 error is defined as probability of x lies in critical region given that null hypothesis is true, equals to probability of null hypothesis is rejected given the null hypothesis is true. And we know when the null hypothesis is rejected, when there is 7 or more than 7 heads. So we can write it as probability of 7 or more heads given the null hypothesis is true. And from this we can also write probability of x equals to 7 given p equals to 0.5, or probability of x equals to 8 given p equals to 0.5. That means there is 8 heads, and or there will be 9 heads. That means probability of x equals to 9 given p equals to 0.5, or there will be 10 heads. That means probability of x equals to 10 given p equals to 0.5. For calculating it, we can get the value as 11 by 64. Now for type 2 error, we know the type 2 error is probability of x doesn't lie in the critical region given the null hypothesis is false, equals to probability of null hypothesis is accepted given the alternative hypothesis is true, equals to 1 minus probability of null hypothesis is rejected given the alternative hypothesis is true. And when null hypothesis is rejected, when there is 7 or more than 7 heads. So we can write it as 1 minus p of 7 or more heads given and the alternative hypothesis is true. And p and the probability of 7 or more heads means the probability of 7 heads, or the probability of 8 heads, or probability of 9 heads, or probability of 10 heads. So we can expand it like 1 minus p of x equals to 7 given p of 0.6 plus probability of x equals to 8 given p of 0.6 plus probability of x equals to 9 given p of 0.6 plus probability of x equals to 10 given p of 0.6. So after calculating this, we get the value as 0.61772.
So that was all about our topic, hypothesis testing. Hope we covered all the concepts of this topic. So I would like to conclude our presentation by saying thank you. And at the critical time of this epidemic, I would like to request you to stay home, stay safe. Thank you.